In March 1989, the skies above Quebec transformed into a dazzling light show. The auroras, usually confined to polar regions, illuminated the night as far south as the Caribbean. But this celestial spectacle was a harbinger of chaos. A massive solar storm had struck, and within seconds the entire Quebec power grid collapsed, leaving millions without electricity for up to 9 hours. This event served as a stark reminder of our modern vulnerability to the sun's whims. Solar storms, also known as geomagnetic storms, are not just beautiful displays of natural lights. They are powerful disturbances in Earth's magnetic field caused by bursts of solar energy. While they can enhance the beauty of the night sky, they also have the potential to disrupt everything from satellite communications to electrical power grids. The 1989 Quebec blackout is a perfect example of how these solar outbursts can instantly flip our technological dependencies into liabilities. The Quebec incident is not an isolated case, but a preview of what might become a frequent disruption as our reliance on technology deepens. As we move further into the 21st century, understanding the power and threat of solar storms is not just about scientific curiosity, but a necessity for safeguarding our technological infrastructure. This essay explores the invisible yet formidable force of solar storms, their impact on our technological systems, and how we can mitigate their effects. If you found this topic fascinating, make sure to like and subscribe to our channel for more content on solar storms and other intriguing subjects. Solar storms originate from the Sun, our star, which is a maelstrom of nuclear energy and magnetic fields. At times, the Sun releases huge amounts of solar energy in the form of solar flares and coronal mass ejections, CMEs. These phenomena send streams of charged particles hurtling towards Earth at incredible speeds. When these particles collide with Earth's magnetic field, they trigger complex changes in the magnetic field, leading to geomagnetic storms. The interaction between these solar emissions and Earth's magnetic field is not merely a spectacle of light and energy. It is a dance between cosmic forces that can have profound implications for our planet. For example, solar flares primarily emit X-rays and ultraviolet radiation, which can affect Earth's ionosphere and interfere with radio communications and GPS signals. On the other hand, CMEs, which are larger clouds of plasma and magnetic fields, can create stronger and more lasting impacts, including long-term power outages and damage to satellites. Understanding these solar phenomena is crucial for predicting and preparing for their potential impacts. Scientists use a variety of tools and satellites, like the Solar Dynamics Observatory (SDO) and the Advanced Composition Explorer (AC), to monitor solar activity and provide warnings. These tools help us grasp the complexities of solar behavior and anticipate the timing and severity of solar storms. The consequences of solar storms on Earth's technological systems can be severe. The 1989 Quebec incident is a prime example where a geomagnetic storm induced currents in long electrical transmission lines, leading to transformer failures and widespread power outages. Similarly, in 2003, a solar storm disrupted satellite operations, air traffic communications, and even the Swedish national electrical grid system. These incidents illustrate the broad spectrum of technologies vulnerable to solar phenomena. Satellites, which play a pivotal role in our communication networks, are particularly at risk. During intense solar storms, the Earth's atmosphere expands due to heating from increased radiation. This expansion increases the drag on satellites in low Earth orbit, potentially altering their paths and shortening their operational lifetimes. Moreover, the charged particles can penetrate satellites, damaging their electronics and disrupting their functionality. On the ground, the risks are equally significant. Long electrical transmission lines can act like antennas, picking up geomagnetic disturbances and converting them into electrical currents. These currents can overload electrical grids and even cause permanent damage to transformers, which are costly and time-consuming to replace. The reliance on digital systems for managing utilities, banking, and emergency services also makes society more susceptible to disruptions from solar storms. As we look to the future, the potential for more frequent and severe solar storms looms large due to the Sun's natural 11-year activity cycle. The next peak, expected around 2025, could coincide with our increased dependency on digital and satellite-based technologies, potentially amplifying the impacts of solar storms. Awareness and preparedness are therefore crucial in mitigating these future risks. Efforts to shield our technology from solar storms are underway. For instance, power companies are developing more robust transformers and implementing smart grid technologies that can respond more dynamically to sudden electrical surges. Satellite designers are enhancing shielding and using more resilient components to withstand solar radiation. Moreover, international collaborations like the Space Weather Prediction Center provide critical data and forecasts to help industries and governments prepare. However, these measures alone are not enough. As our infrastructure becomes more intertwined and reliant on precise technological processes, the potential for significant disruption increases. Therefore, continued investment in research, infrastructure hardening, and public awareness is essential. Only through a comprehensive approach can we hope to protect our technological society from the whims of solar activity. The threat posed by solar storms is both real and significant. As we have seen, these celestial events have the power to disrupt our technological systems, from power grids to satellites and everything in between. The incidents in Quebec and Sweden are stark reminders of our vulnerability and the need for vigilance and preparedness. Moving forward, it is imperative that we not only invest in protective technologies and infrastructure, but also in education and research. Understanding the science of solar storms and disseminating this knowledge widely will empower individuals and communities to better prepare and respond to these natural events. Furthermore, international cooperation in monitoring and forecasting solar activity can enhance our collective ability to mitigate its impacts. In conclusion, while we continue to marvel at the beauty and power of the sun, we must also respect its potential to disrupt our technological world. By fostering a culture of preparedness and resilience, we can ensure that our society not only survives but thrives in the face of solar storms. The time to act is now, to safeguard our future against the next solar surprise.